Now we're going to develop several examples of using the Chinese remainder theorem to solve systems of linear congruences. So our first example is to solve the system of congruences given by x must be equivalent to -3 mod 6, but also equivalent to 2 mod 11, but also equivalent to 0 modulo 13 and -1 mod 7. So we actually have four equivalences to solve here. So just to clarify our notation, we're using b sub I to represent the target values of -3, 2, 0, and -1 respectively, little n sub I to represent the modular bases that correspond to those target values, 6, 11, 13, and 7. So capital N is the product of all of the bases, which turns out to be 6006. Capital N sub I is all of the bases except for the one at the ith index. So capital N sub 1 would be little n sub 2 times n3 times n4, 11 times 13 times 7, which is 1001. Similarly, capital N2 is the product of all the little n's except for the second one, and so forth. And remember, the Chinese remainder theorem is only going to apply when all of the bases are co-prime. So 6 and 13 are relatively prime, 11 and 7 are relatively prime, 6 and 11, 13 and 7, 6 and 7, etc. You have to check every pair of bases against one another. In this particular case, 11, 7, and 13 are different primes, and then 6 is the only base that isn't a prime, but its prime factorization does not involve 7, 11, or 13. Okay, so continuing with our solution, once we've computed these capital N's, we have to start finding inverses. Specifically, y sub I is capital Ni inverse modulo little ni. So we have to compute capital N1 inverse mod little n1. Capital N1 was 1001 and little n1 was 6. And at first, the appearance of this 1001 inverse seems imposing, but since we're working modulo 6, 1001 is equivalent to 5, which means 1001 inverse is equivalent to 5 inverse. So we really only have to find a number that when I multiply it by 5 is equivalent to 1 modulo 6. -1 works. 5 is equivalent to -1, and -1 is its own inverse. So y1 is anything equivalent to -1 modulo 6. Similarly, we need to compute y2, 546 inverse modulo 11, but we can then reduce 546 is equivalent to 7 modulo 11, so 546 inverse is equivalent to 7 inverse. 7 times what is equivalent to 1 modulo 11? 7 times 8 is 56, that's 55 plus 1. So y2 is anything equivalent to 8 mod 11. Y3 is something equivalent to 462 inverse mod 13. We reduce that to 7 inverse mod 13, and we see pretty quickly that's just 2. 7 times 2 is 14. And finally, y sub 4, we need to find 858 inverse mod 7. We reduce that to 4 inverse mod 7, which again is pretty quick. Also anything equivalent to 2, but this time modulo 7. So now that we've computed our inverses of the capital N's mod the little n's, we simply compute this sum of BI, capital Ni for all terms and add that together. So our b's were declared at the beginning, -3, 2, 0, -1. We've computed our y's, and we're just going to go ahead and pick -1, 8, 2, and 2. Now, y1 can be anything equivalent to -1 modulo 6. So I picked -1 here. But I could have picked any integer equivalent to -1 mod 6. For example, I could have picked a 5 here and everything would have worked out just fine. But in any case, once we compute all of these products and add up the terms, we got 10,023. So all solutions are given by x is equivalent to 10,023 modulo capital N, which was 6,006. And for convenience and prettiness, we can just reduce 10,023 mod 6,006 is the same as 4,017. Observe that in the third term, we were trying to solve x equivalent to 0 modulo 13, which means when we computed all of this inverses and then products and added it together, there was a b sub 3, in other words, a 0 multiplying other stuff here. So since b sub 3 was 0, y sub 3 ended up being kind of irrelevant because it was going to be multiplied by 0 anyway. So if you have some zeros thrown in, it does save you time computing inverses. If you're trying to make x equivalent to 0 with respect to one of your bases, that's an inverse you don't have to find. So that might be a little convenient. All right, let's now try to find the smallest positive solution to the following three equivalences. X equivalent to 4 mod 5, x plus 5 equivalent to 1 mod 6, 3x minus 1 equivalent to x plus 4 mod 7. All right, the bases are relatively prime. 5, 6, and 7 are certainly all relatively prime to one another. But before we can apply our technique, we need to get each line to just look like x equivalent to something mod the base. First line is just x equivalent to 4 mod 5. That's already fine. However, the second line has x plus 5 equivalent to 1. If we subtract 5 from both sides, then we get our desired format, x equivalent to negative 4 modulo 6. The third line, however, is going to take slightly more work. If I add 1 to both sides, and then subtract x from both sides, we get 2x equivalent to 5 mod 7. Now this x is being multiplied by 2, and I don't want the 2 there. I can't divide by 2, but what I can do is multiply by the inverse. Since 2 and 7 are relatively prime, 2 has an inverse, which turns out to be equivalent to 4 modulo 7. So if I multiply both sides by 4, that's the inverse of 2. It cancels this out, leaving behind just x. 4 times 5 would be 20, which modulo 7 I can reduce to 6. So I end up with the following three equivalences. The first was already x equivalent to 4 mod 5. The second, I subtracted 5 to get x equivalent to negative 4 mod 6. The third, I had to manipulate into the form 2x equivalent to 5, but after multiplying by the inverse of 2 mod 7, which was equivalent to 4, we got x equivalent to 6 mod 7. So now I have three modular equivalences, all of the desired form. We can proceed with our earlier technique. So we let capital N be the product of all the bases. 5 times 6 times 7 is 210. Capital N1 is the product of the ones except the first. Capital N2, the product of the bases except the second, etc., etc. We now need to find inverses. For example, y1 is capital N1 inverse mod little n1, or 42 inverse mod 5. 42 modulo 5 is equivalent to 2. So 42 inverse is the same thing as 2 inverse. And 2 inverse mod 5 is equivalent to 3. I'm kind of leaving out some of the writing, okay? We should be getting more and more familiar with these techniques with every example. Y2 is going to be capital N2 inverse mod little n2, or 35 inverse mod 6. However, 35 is equivalent to 5 mod 6, and 5 inverse is also just equivalent to 5. Okay, I spotted a little typo there. That subscript should be a 2. And finally, y3 is 30 inverse mod 7, which turns out to be equivalent to 4 mod 7. Now that we have all of our inverses computed, we simply compute bi, yi, capital Ni for all of the various equivalences. All of these turn out to be 524 mod 210. However, we were asked to find the smallest positive solution, so I need to reduce 524 modulo 210, and I get 104. So 104 is the smallest positive solution to these three equivalences. You can double check your answer if you want by checking that it indeed does solve all three of the original, and because the bases are relatively prime, we know from the Chinese remainder theorem there is only one solution modulo 5 times 6 times 7, which was 210. So there's only one solution mod 210, and we found one solution that was less than 210. It must be the smallest positive solution. More examples. Show there are no prime numbers p which solve both of the following, equivalent to 5 mod 10 and also equivalent to 4 mod 11. Well, set aside the question of whether they're prime or not, any solution by the Chinese remainder theorem will be seen to be of the form 6 mod 110. You have to go through and do the work, of course, but it's only two equivalences. It should be fairly fast. And you'll see any solution must be equivalent to 6 modulo 110. But if p is equivalent to 6 mod 110, it's a multiple of 110 plus 6, and we very quickly see that 2 can be factored out of this. So 2 must be a factor of p. If p is prime and 2 is a factor, then the only prime that has that property is 2 itself, but 2 is not actually equivalent to 6 mod 110, nor is it equivalent to 5 mod 10 or 4 mod 11. So there can't possibly be a prime number that solves both of these equivalences. Now, alternatively, just from the first equivalence, p is equivalent to 5 mod 10, you can get that p must be a multiple of 10 plus 5, from which you can derive that 5 must be a factor of p. That is not immediately an obstruction to the first equivalence. If p is simply 5, that's a prime number, and it is equivalent to 5 mod 10. However, 5 does not satisfy the second equivalence. So there's another way that you can see there are no primes that solve both. Another example, you have a neighbor, they have a cardboard box full of peas, and you want to count the peas. Well, they want to count the peas, and they've roped you into doing it. So, in fact, they've offered you a quarter. That seems like good money for pea counting, so let's get to it. Unfortunately, you can't count higher than 20. It's just not working. There are definitely more than 20 peas, okay? But that quarter, it's shiny and you want it. So you count out 20 peas at a time because that's what you can do. And every time you count out 20, you put them in a separate box. However, at the end, there are 3 peas left over. You do it again and you count out 19 peas at a time. If you take the entire collection of peas and count them out in multiples of 19, there are 16 left over at the end. And when you count them in groups of 17, there are 14 left over at the end. When you count in groups of 13, there are 9 left over, and when counted in groups of 11, there are 2 left over. So you then confidently announce your neighbor has 65,243 peas. How are you so sure of your answer? Well, if x is the number of peas in the box, because we counted them out in groups of 20 and had a remainder of 3, x is equivalent to 3 mod 20. When counted out in multiples of 19, there was a remainder of 16. When counted out as multiples of 17, there was a remainder of 14. The remainder of 9 when counted out in 13s, and a remainder of 2 when counted out in 11s. So whatever the number of p's is, it must satisfy all 5 of these modular equivalences. Where were we? We had the following 5 equivalences to solve. Observe, the bases are all pairwise relatively prime, which means we can use the Chinese remainder theorem. This is, by the way, why I didn't count out the p's modulo 18 or modulo 16. I wanted to make sure that the bases I picked, 20, 19, 17, 13, 11, are all pairwise relatively prime. So we can apply the Chinese remainder theorem, we do a bunch of work, and we eventually get x as an integer which is equivalent to 65,243 modulo 923,780. But earlier we didn't just say that the number of p's was equivalent to 65,243 modulo 923,780, we said it was equal to 65,243. How did we get this extra leap? There are, in fact, infinitely many integers that are equivalent to 65,243 modulo 923,780, but at the very least, we can assume we were counting out positive p's, not negative p's. Thankfully, we didn't have a box full of anti-p's to count. So the answer is presumably positive, so we can throw out all the negative solutions. And as we all know, your average dried pea has a weight or a mass of about 0.2 grams. And 923,780 of them would therefore be about 200 kilograms. We started out counting peas that were in a cardboard box, and I don't think we can fit 200 kilograms of dried peas into a single cardboard box. So the solution should be a positive integer, but it shouldn't be as large as 900,000. So the only integer equivalent to 65,243 mod 923,780, which is also less than that base of 923,780, is equal to 65,243. That's got a total mass of about 13 kilograms, and I can believe that we had 13 kilograms of peas in a box because we've all been there. Now, this problem is actually similar to historic formulations of the original Chinese remainder theorem problems, counting things modulo different bases, but it's also used in a modern situation for a technique called range ambiguity resolution in radar systems. If you have different pulses from radar systems that are kind of interfering with one another, or very, very frequent pulses from the same radar system is more likely, can you determine how far something away is if you don't know exactly which pulse of the radar is being reflected back to you at what time? That's range ambiguity resolution, and it is a Chinese remainder theorem problem.